All right. Hello, everyone. Welcome. We're officially, in it. We're past that drop deadline, so things get a little bit more clear, I guess, in terms of who's and what. So that's nice. Logistics-wise, reminder: the quiz opened up for units and vectors. Opened up this last Friday, and you all have till this Saturday to complete it. So hopefully, you start going through the problem set and all that good stuff. Remember, these quizzes you get 4 attempts on, which is like plenty. I say plenty. It's a lot of attempts. It's 5 questions. So if you miss one question, it does, ding things down. But that's why I get 4 attempts. So use any and all resource. These quizzes are to help you monitor your learning. That's the reason they exist. They give a grade kind of associated with that, but then they also functionally serve as a way for you to kind of monitor, am I understanding, for example, quiz 1, am I understanding units and vectors? There's the 4 attempts, so it should be pretty low stakes in terms of use any resources and all resource, ChatGPT, other people, whatever. But at the end of the day, make certain it's actually helping you monitor your learning. Make certain you're going through the problem sets. The quiz is not sufficient as practice. You cannot rely on the quiz as all the practice. If you only do the quizzes, that is only going to work for you if you already know physics. That's just the reality. It is not enough practice for 90-95% of people. You have to be going through the problem sets exist to give you as much practice as I think is kind of, as if you go through all the problem set, that is definitely enough practice for people. So, anyway. That's the philosophy of this class. If at any point you're like, things aren't going well, that's always the first question you'll ask. How's the problem sets going? So, anyway, do that. Also discussions start meeting this week, so make sure you attend that, do the questions, all that good stuff. That should go really smoothly. And then last week, so, we talked about units and vectors. And then I told you all I'd upload the solution. So this boat problem, it is in the problem set. We kind of quickly chatted about it, but the full worked out solution is uploaded. So you can check it out if you're stumped. Reminder to you all, when you're solving problems, do not immediately have the full worked out solution next to you as you're solving it. That is not helpful. Only refer to the full worked out solution if you're stumped. Because otherwise, again, it's like watching someone drive and saying, yep, I can do that, and then leaving it there. You need to try it for yourself. Learning is a lot like working out, where if it's not hurting, you're probably not gaining many muscles. That is the reality with working out. If you're not feeling any burn, if you're not feeling any strain, you're not really gaining any muscles. You're not really burning that many calories. That is the reality. Learning is the same way. If it's not making your brain hurt a little bit, either it's really trivial for you because you already know it. If you're really strong, you can lift a bunch of weights. You don't need to keep working out to lift a bunch of weights. If you're really good at physics, yes, it's not going to hurt your brain much because you're not having to learn. But if it is making your brain hurt, that just means that learning is happening. It's not fun. I say it's not fun. Part of it's cool because you're learning new things and stuff like that. But yeah, it's subjective, I guess, and whether you enjoy that feeling of mental load or whatever. It's part of learning. It is how it is. That's always true of anything. So keep that in mind. And then again, remember, last logistics update. I sent out an announcement. There is 3 places on campus where you can get one-on-one help with things. My office hours are one of them. The other one is the help room. And the last one is the Sark tutoring. So let me check one thing because I make sure my office hours are correct. So I had people show up today, so that's good. But I did, in the past, people pointed out that my office hours location. So my office hours, reminder to you all, they're in here, but my office location is PSB 134. I think I'd had a typo in the past. I thought, good, that's when that meets. Yeah, I didn't update this. So my apologies if you all tried to find my office and you're like, why is it the room that we meet in? It's not. My office is located in PSB 134. Remember, this is, if you go outside this building and you go around the loop counterclockwise, it's next to the park. It's past the health services building. And then my room is in the back left of the building. Go in the front door, back left. You'll find me. So I've already had some people coming by. Makes my life more entertaining. I enjoy when people come by and actually get to work with people. So great. My stuff is office hours exist. There's also Sark tutoring. I posted the times for that. That's courtesy of them. They're great undergraduates who've gone through the course and done well. Additionally, there is the help room, which is staffed by a variety of people at a variety of times. Just check the schedule. This is also in Physical Sciences building, same place as my office, but it's the first door on the left. Literally walk in the front door, first door on the left. Super easy to find. Holds like 20 people. You can go to any of these people. You can go to Robin. Robin took my 2048 class a year ago. So Robin's one of my previous people. Emelina also took my 2048 class in the fall. Leo was my LA. The rest of these people I don't know. But they're all great, I'm sure. They're a great resource. They are undergraduates who have gone through the course and done well. And in my opinion, undergraduates are some of the best people to go to for assistance because they are the closest in proximity to you, meaning they know a lot of the challenges that you have gone through. Sophia also, she's the LA for my class. She's a biology major. So these people are a variety of majors. They're not all just like engineering majors. Variety of majors and perspectives. So you can go around, find people you're comfortable with, different days and times. Anyway, so many resources to get help with that UCF offers. Take advantage of them. They're useful. All right. So great. We did all this. I had one last question that I didn't get to. It's in the problem set. I am not going to test you all on this question. Don't expect a question like this in the test, but it is a useful question, and I'll talk about why I think it's useful. Spend 30 seconds. I don't need you to necessarily calculate it, but I want you to think, you can try to calculate it if you want. Think about how you would calculate this. That's the benefit of this. That's the reason for this problem. Approximately how many heartbeats are there in a lifetime? Spend 30 seconds. Think about it yourself. Talk to the people next to you. I don't care. I just want you thinking, how the heck would you figure this out? Think about it. Talk about it. All right, and you know what? We're going to try this out as well. I forgot I could do this. Do I want to do this? Maybe not. I don't know. Time-wise, I can actually ask a question to Top Hat or whatever. I'll hold off on that for the sake of time. All right, so how do you do this? We call this a back-of-the-envelope calculation. Basically, it sounds like exactly what it is. It's a calculation you can do on the back of an envelope. It's a really quick approximation that you can use because this is a super useful skill. Like, do you need to know how many heartbeats in a lifetime? No. But this is just a medical context problem for this. Another example of a problem like this would be, how many patients does a Winnie Palmer have in a day? You'd be like, how the heck do I figure that out? There's approximations you can make. So we'll do this one, and then I'll go through that example of like how I would go and figure that out without Googling a bunch of information. So, average heartbeats, somewhere around 80-ish. Let's just say the average person has about 80 beats per minute. You could say 70, you could say 80, you could say 90, whatever. The number, we don't need to, this is not being super precise. It's approximately. So 80 beats per minute. And then let's just say the average person lives for 75 years. We got to get some just guesses, approximations, things that you might know that would help us answer this. So then we just go through this and we say, well, if there's 80 beats per minute, we then just multiply that by 60 minutes in an hour. And then we multiply that by 24 hours in a day. And then we just multiply that by 365 days in a year. And then finally, we multiply that by 75 years. And it gives us, and we put this little squiggle stands for approximate. It's not a normal equal sign. It's got a little squiggle to it. So 80 times 60 times 24 times 365 times 75, we get roughly 3 times 10 to the 9, 3.11. It really doesn't matter. I'm not going to pretend like this is precise. Great. And that took us 30 seconds to do. It's not a precise answer. This is not true of every single person. This is in the ballpark. Order of magnitude is what we say. Within, somewhere, it's a billion, somewhere in the billions, probably, give or take, depending on the person. So, let's think about the Winnie Palmer example. How would I do this there? I'd go to Winnie Palmer, and I might look at the windows of the building and say, each window probably represents a room. And then I kind of maybe on one floor count roughly how many windows. And if that's one side of the building, I say, well, the building probably has 4 sides. And then maybe I chuck some extra rooms in there because I'm like, there's probably some on the inside. I'll guess how many. That gives me for one floor. Then you just count how many floors, multiply that by that. That gives you a sense of how many total rooms that can hold patients. Then you guess that maybe those are 60 or 70% occupancy. I have no idea how busy a hospital is. You have a better idea than me. You multiply that by 0.6 or 0.7, and maybe they can fit more than one person. Anyway, you take all this information you might know, and you get a rough answer. And this is super, super useful because you don't always have time to get all the information. But sometimes you just want to get a sense of what the right answer is. So I'm not going to test you on this skill. I don't even know what you would call this skill. I don't know what the name of it is. Being able to approximate things, I guess. But you'd be surprised at how often stuff like this can come up. If you want to get how tall a tree is, you're like, how the heck am I going to do that? Well, if I know I'm 6 feet tall, I just say, how many of me does it take to fit up the tree? And that gives me a sense of how tall the tree is. There's so many cases where if you just take something you can kind of work from there and get an approximate answer for something you don't know. Useful skill. I mention it now. Maybe I'll come up with more examples of this. Again, I'm not going to test you on this, but I want to mention it because it is a critical thinking skill that you might secretly kind of learn as time goes on, but I'm going to explicitly mention it now because generally it never, I don't know where you would learn this in any class. Just like a life skill almost in a lot of ways. So it's there. I thought it was interesting and useful, so I chucked it here. So there you go. That covers units and vectors. Main takeaways from last week was don't forget your units, both in terms of on your answer and when you're reading a problem. The units tell you what is 3. If you put a unit after it, it means something, and it tells you what it means. Make sure your stuff's in base units. Vectors are arrows. That's all a vector is. A vector is an arrow. Vectors are just arrows, and they have magnitude, direction, and magnitude. And remember, we figured out direction is given by an angle, generally with respect to positive x-axis. Not required, but that's often the default. And this last one is going to come up in many weeks ahead. Anytime we're working with vectors and you're adding things together, you have to break them into x and y components. That is a bread and butter skill. And if you're not, by the end of my class, if you're not decent at it, you're going to have done very poorly on a lot of things because so many things use it. It's just a foundational skill to solving so many different types of problems. So I practiced it during the first week. We're going to continue practicing it. We're going to continue seeing it, but I spend the time now just to give us hopefully a somewhat of a foundation that we can strengthen as the semester goes on. All right. So today we're going to get into 1D kinematics, which is a really fancy sounding word that's just 1D motion. That's all kinematics. Kinematics is a study of motion. That's all it is. Sounds really fancy. So we're going to introduce, today it's going to be we got to introduce some jargon. We got to be precise in what our words mean. Science is all about precision. When you're going to the moon, you got to know the exact numbers. And, even with being a doctor, there's a reason they take so many tests and things like that. We got to be precise. We want to figure out things exactly. So this is a study of motion, and so we got to be precise in our terminology. So we're going to define those words, measurements. They're going to be position, velocity, and acceleration. Position is where you're at. Velocity is how fast you're going. And acceleration is how much your velocity is changing. These are all vectors. So position, we're going to find is not just where you're at, but in what direction, how far away you are from something, angle, magnitude, all that good stuff, x, y. Velocity is not just how fast you're going, but how fast you're going and in which direction. Acceleration is not just how much is your velocity changing, but in which direction, right, left, up, down, all that good stuff. Probably Thursday we'll actually get to the equations. I'll show you all them, just so you don't have shell shock on Thursday. And in fact, I'm going to move this. We're also going to work with graphs, because this was probably one of the most challenging thing with this. You all read a bunch of graphs, but position versus time graphs, velocity versus time graphs, learning how to read those and things. So it's going to be good. It's going to be useful. I think I may have mentioned this. I don't know if I did or didn't. The beginning of the semester is, in my opinion, the hardest because the skills and the things I'm teaching you are the foundations for the rest of the class. So in this beginning, there's a lot. I'm covering the problem-solving process. I'm covering vectors. I'm covering the definitions of position, velocity, and acceleration. And the rest of the semester, we're then going to use those. But because it's so many things all at once in the beginning, it can be the hardest part of the course. And there's just no getting, like, this is the stuff that we have to build up. So I say that as an encouragement. If the beginning is like, oh my goodness, it's so many things, it does get smoother. Test 1 scores tend to be lower than test 2 scores because there's a bunch of new skills I'm trying to teach you all. And by the time we get to test 2, you'll be better at those skills, and test 2 has less vectors on it. So, twofold there. So just, keep that in mind. Gives you some peace of mind. The average for test 2, I think, is usually like 5% higher or something like that. It's like most classes. The first test is generally the hardest test because you have to learn how the course works and all that. These things. All right, so I already said this. Kinematic, study of an object's motion. We need to be precise with our definitions. You've probably heard these words before, but I'm going to make certain you understand the nuance that we need to understand to use them correctly. Be great. All right, first question. Here's Demo Duck. He's a staple of this class. He's called Demo Duck because he's a demonstration duck. My brother gave him to me for Christmas one year, and he's been worked hard. He'll get thrown across the room and all sorts of things. There he is. All right. So this one I am going to ask as a question on here. So it's going to be a word answer. Anytime I do anything other than multiple choice, as long as you answer, you get all the points. Really straightforward, really easy there. So if you're online, you're probably not going to see this, but I don't know. Pick something. Demo Duck. Gosh, I don't really have a webcam. I have set him on a table in the middle of the room. My question to you all is, what is Demo Duck's position? I'll go ahead and tell you the description I just gave is not sufficient. So yeah, talk with your neighbors. Come up with a good definition of where its location is, and then we'll look see what you all have said. Don't worry, none of these, there's no names attached. Whenever I look at the responses, there's no names. And the goal is to start having these as part of your grade Thursday. So I'll kind of check and see how the enrollment's going. But make certain you sign up for this by Thursday. I will, between today and Thursday, show the grades on web courses so you can see if everything's working the way it should be. I'll sync them on over. But yeah, make certain you sign up for this. All right, we'll go like 10 more seconds just to get as many people to respond as possible. All right, and I'll close it out in 5, 4, 3, 2, 1. So good, we got most people are here. Heads up, I do stream the class. You can answer these top hat questions remotely if you're watching the stream. However, whenever you hear me say, hey, you got 10 seconds left, if you hear that on the stream, that was 30 seconds ago. Be warned, I've set the stream to low latency, but the reality is this has to get to your device. And the fact that it even gets there with only a 30-second delay is its own miracle. Like, technology is crazy. But yeah, you don't want to wait. Like, if you hear that on the stream, that was 20 seconds. Like, the delay might be like 20, 30 seconds, depending. It varies. So to that end, you should get it on your phone like almost instantly. I mean, the fact that you all get it on your phone here instantly, it basically travels the same distance, pings off the tower, and whatever. There's a whole process with that. So as long as you're kind of doing it on your device, but just if you're doing it remotely, answer quicker than slower, because don't wait for me to say 5 seconds left or something when you're online. Just a heads up on that. I don't want people to miss points because of that. Is the thing. Anyway, let's look through these. Again, there's no names. All right, we got upright and forward, neutral, center of the desk, on the desk, idle or in rest, closer to sea level than me. Interesting. All right, so notice that there's varying complexity here, and I am going to start with some of the simpler ones, and then we'll kind of look at more ones. So on the center of the desk. Okay, so great, we have this desk. So as long as we know it's a desk, that's good. But you could say this marker is also at the center. That gives a pretty big range here. So it's close, like that gives us a sense of it, but it's still, remember, we got to be super precise. My goal with this answer is that if I took the duck off the desk, you'd be able to tell me exactly where to put it. That's the precision we're looking at, that I can put this thing exactly where it started with. We need to be precise in physics. So to that end, facing forward, middle of table. That gives too much range. Let's see. Front of class, left side, still there. So what I'm looking for here, 0, 0. That's interesting. I appreciate that one. That one can be right. So to that end, to be precise, we need numbers. We need measurements. And something that's interesting that I do appreciate is you all gave a reference. You didn't just say at the center. You may have said at the center of the desk. You referenced something. So something that's going to be a really common theme in today's class is we call it a reference frame, or another kind of phrasing of that is, where's your origin? What are you measuring with respect to? So in this case, we're going to find that position. Shock and awe, we're in a 3D world. We need 3 numbers, X, Y, Z. And we need units. So I might say, if I want to be precise, I'm going to make this corner where I measure from. Everything is going to be measured from this corner. So I might say 30 centimeters to the right of this corner, 20 centimeters in front of this corner, and then 0 centimeters above that. And that would give me a precise location. And so there's 2 aspects there that are important when you're talking about position. You need multiple dimensions, you need numbers, and you need to say what you're measuring with respect to. You can't just say it's 2 centimeters away, because 2 centimeters away from something describes a point on a sphere. 2 centimeters away, so let's just demo duck. If I said demo duck was 10 centimeters away from this marker, that could be here to the top right of it, that could be above it, that could be to the right of it, that could be in front of it. 10 centimeters away is anywhere on this, it makes a spherical shape. So we need 3 dimensions to get a precise location, and then we're going to see that in class. Now, to spare you all, we're just going to work in 2 dimensions at most in this class, okay? We're not going to be able, if you can do it in 2 dimensions, you can do it in 3, but the real world is 3, so I just mentioned that. Where an object is located relative to a reference frame. Reference frame is what it sounds like. It's what you reference. It is, if I say it's 5 meters away, from where? Generally, we'll say that's where we began. We'll say the origin. Where's the origin? Where is 0, 0? That's the question. And that's going to come up in our problems and things like that. It's a subtle thing, but it makes a big difference in what your answer is. So, there you go. It is a vector because, again, it's got an amount and a location. It's got a direction. It's not just 5 meters away. It's 5 meters in the X direction and 3 meters in the Y direction. And that gives me a precise location. We're also going to see today, positive is to the right, negative is to the left. Negative doesn't mean a small number. Negative just means the left. Positive means the right. When we're talking about vectors, that's going to come up again and again and again and again and again and again and again. And I'm even going to put that here because it's going to be such a common trend. Every single vector we talk about today, positive is to the right, negative is to the left. So, positive, if we're in the X direction, in X direction, positive is to the right, negative is to the left. It's exactly what you want. Hopefully no one wants negative to the right. If you do, you're just going to confuse everyone. You can define your reference frame, but that gets really complicated. You have to communicate more. This is the default. It's what people are used to. Eventually, when we start talk about the y direction, positive is up and negative is down. Again, hopefully matches what you'd like. Okay, position. The simple fundamental description of where something is located, and moving forward, every single thing after this is going to be based on position. Velocity, acceleration, they all come from measuring position. Position is there's not many things you can actually physically measure. That sounds like, what? You can measure lots of things. When you measure velocity, the reality is you're measuring position and dividing it by time. When you're measuring acceleration, you're measuring position and seeing how it changes twice. So, whatever, I won't get too much into that. But great, the next one is displacement. What is displacement? Take your final position, take your initial position, subtract the two. Displacement is the difference between the final position and the initial position. Notice we don't care how you got there. I don't care how you got from the beginning to the end. I just care about the final point and the initial point. So it actually makes it really simple. You don't care what happened between it. You just care beginning and end. And for one dimension, you just do the x's. You combine the x's. When we get to 2 dimensions, you'll do the x's together and the y's together. You got to keep them separated. You cannot combine x's and y's. But yeah, displacement, final x minus initial x for one dimension. Nice and straightforward definition. But here's where I'm now going to... So you might have heard the word displacement before in a general sense. You know, people have been displaced. That means they got generally they left where they lived. That's kind of the everyday use of it. This is what it means in science. This is what it means in physics. Unit is meters. That's a base unit. If you see centimeters, convert it. If you see millimeters, convert it. If you see kilometers, convert it. Just get things to base units sooner than later. All right. Key points here. Distance is also a word you've heard. Distance and displacement do not mean the same thing. 2 words that both start with D don't mean the same thing. Displacement is a vector, so the direction matters. It matters where I started and where I ended. Distance is a scalar. Distance doesn't care about where you stopped and ended, and the path that you took matters. We're going to almost exclusively use displacement, but there is a case for using distance every now and then. So the example here, distance is like if you have a smartwatch or if you have an odometer. So smartwatch tells you how far you've walked in a day, how many miles or kilometers. It says that. That's distance. It doesn't say which way you've walked. It doesn't say whether you walked left or right or north or south or east or west. It just says you walked this many miles. That's distance. It keeps track of it. If I walk back and forth again and again, that number will get higher and higher and higher and higher. Fantastic. Displacement is not that. Displacement only cares about where you start and where you end. And so I'm going to pick an extreme example to prove that point. And I'm going to leave it as an open question. I have to clarify, if you live in just one home, because if you live in different homes, this answer varies. If you live in just one home, you start at the same house and you go back to that house at the end of the day, what is your displacement from the beginning of the day to the end of the day? Chuck it in here. You can figure it out. There is a right answer. I am making some assumptions about your daily habits. I'm assuming you have the same daily habits as the vast majority of people, though things vary. So that's why I didn't make a choice answer. Maybe 30 more seconds. I don't want you all to overthink this. Yeah. Sure, yeah. For sure. And these ones, because I don't really care about, again, as long as you respond, you get the right answer. I'm not as worried, but I'm going to leave it open. I'll actually leave it open. Look at this. We got a bunch of different answers. Don't forget your units. Someone put 3. 3 what? 0 what? Same thing. But look, you notice a lot of people with the same answer, 0. So that gives us an indication. Maybe they're right, maybe they're wrong. Let's go with a definition of displacement. Displacement is this: final location minus initial location. So you just say, where do I start every day? Generally in your bed. That's what I was like. I'm making some assumptions here. You start your morning in your bed. Where do you end your day? I'm assuming you end your day in your bed. Assuming you sleep in the same place every single day, your displacement every single day is 0. 0 meters. Don't forget your units. It doesn't care. Who cares what you did that day? Displacement doesn't care. Displacement is where do I start? Where do I end? I don't care what happened in between. And you may say, how is this useful? We're going to see uses of it. Trust me for now. I picked an extreme example to kind of just get the idea across of what displacement is. But this is it. Where do I start? Where do I end? I don't care what you did that day. You could have stayed in your bed the entire day. Displacement 0. You could have gone and traveled 2 hours away and then traveled 2 hours back. Your displacement is 0. You only care about where you start and where you end. That's how displacement works. So, definitions, all that good stuff. All right, let's try ones that are a bit more maybe interesting. I don't know. None of them are going to say bad. I'll close this one. Again, there's no right answer, no wrong answers. You get it as long as you answer it. This one does have a right and wrong answer. That's any multiple choice question. I use these for when there's a right or wrong. That's really easy to define. Or if I don't want to give away too much, I'll use the response. All right. Car goes around the roundabout. Roundabout's the things that you go in a circle. They're more efficient than stoplights, all that good stuff. The roundabout's got a radius of 20 meters. You go all the way around the roundabout. What is the distance traveled? Is it 20 meters? Is it 125.67 meters, 0 meters, or 40 meters? Distance. Try it out. Talk to your neighbors. Anytime there's these questions, anytime I give you all a question, chat with people. If you and your neighbor have different answers, one of you is wrong or both of you is wrong. All right, give you like 20 more seconds. All right, in 5, 4, 3, 2, 1. Great. All right, so we draw a picture. Pictures help. You went in a circle. We started here. We went around. Remember, distance, the path matters. Distance is how far you traveled. It's not about the start and the end. It's literally just how far did you move. If you have an odometer, it's how much did your odometer go up. If you have a smartwatch, it's how much did it track your mileage, all those good things. So then you just ask yourself, what's the path that I took? It's a circle. How do I find the distance on a circle? That's called the circumference. So to that end, we just plug in the numbers. Now, there's only one answer here that's possible. Even without a calculator, you can automatically figure out what the answer is because 2 times 20 is 40 times pi is a number bigger than 40. There's only one answer here bigger than 40. This is strategies you can use on tests and things like that to automatically, I don't need a calculator. Like, yes, you can plug this in, plug it in, and you'll get this answer. But these are test-taking strategies that you can rule out a lot of answers on multiple choice. Rule of thumb in my test, you can at least rule out 2 of the answers without doing anything in the calculator. If you have a sense of what's going on, if you have a sense of the equation, that's useful. Helps you check your work. If you got an answer that was 20 or 40, you can see it, throughout the pi. Woohoo. All right, so there we go. How'd we do? Ooh, we got different answers, but good. I'm glad I asked it. So, distance, path matters. Don't worry. Remember, you get 80% of the points, even if you don't get the right answer. Let me rephrase that. You get all the points as long as you answer. You get extra credit, the tiny bit of extra credit if you get it right. So, no downsides to missing a question. Low stakes. All right. Car goes, same exact question. What's the displacement? Same exact answer choices. The displacement 20 meters, 125.67, 0 or 40. All right, give you all 10 more seconds. In 5, 4, 3, 2, 1. All right, so displacement. Here's my circle. Displacement, great. We're still doing this path, but I start and I end at the exact same spot. It's the same problem of like, what's your displacement each day? The answer is 0. You only care about where you started and ended. So these are easy, like on a test, I will ask a mix. So on your all's test, about 40% of the problems will be questions, conceptual questions like this. You got to be careful on the wording, on stuff like that. That like, it's one of those, do you know what the words mean? So expect that there could be a problem like this. Conceptual questions are often the quick questions. Doesn't mean they're necessarily easy. You got to be careful. It might be just one of these like a single word. If you mix up distance displacement, you get a different answer. And that comes to our language has to be precise. There's not that much vocab in this class. Like I'm not going to do something mean like this where it's do you know what the word means, definition, stuff like that. But trust me, you are going to need a lot of practice with displacement. It is one of those things I do need to know. You know what it means, and great, y'all do. Easy peasy. So there you go. There's a sense of that. Okay. This one I'm not going to have you all respond to, but I want you to think about because it's an interesting question. You're sitting in your chair right now. Why is a possible displacement not 0? So yeah, think about that. It's like what? Why would it be possible? You're in your chair, you stay in your chair. You don't get up and move around. You stay in your chair. Why is it possible for your displacement to not be 0? All right, who's got some ideas? Who's got a clever idea? Yeah. The Earth is rotating. So yeah, that gets to what is your reference frame? If your reference frame is this room, you're not moving. What if your reference frame is the sun? In that case, you're attached to the Earth is moving, i.e. you're moving. It sounds silly, but this is one of the things in physics. If you're doing, here's the sun, here's the Earth. After a second passes, the Earth moves. It moves a lot. The Earth is moving really fast. Therefore, you're moving very fast relative to the sun. You're not moving very fast relative to everything in this room. Reference frame matters. This is the point of this question, is to remind you all that reference frames matter. And depending on how you define your reference frame, you can get different answers. Generally, our reference frame is the Earth, but if you do space stuff, it's not. And there's all sorts of different reference frames. Another easy example of this is if you're sitting in a car, if you close your eyes and you're going 60 miles per hour, you won't actually be able to feel that you're going 60 miles per hour, assuming the ride is a very smooth ride and all that kind of jazz. You all can't feel that the Earth is moving because everything around you is stationary and moving with you and all that. When you're in a car or a train, and if you're going 100 miles per hour, assuming it's a smooth ride, there's no bumps, you can't tell that you're moving. If you looked at the ground, it doesn't look like you're moving. You look out the window, oh, look, you're moving. Reference frames matter. Okay. Physics things. All right. Mathy things. Position of a particle along the x-axis is given by this equation. X of t equals 4 minus 2t. At what time does the particle cross the origin? That's part A. And then what is the displacement of the particle between t equals 3 seconds and t equals 6 seconds? Before I even want to start this, the biggest challenge to this problem is understanding this representation of position, and then connected to that is making a graph of it. So we'll spend a little bit of time thinking about that. This equation, x of t equals 4 minus 2t, anytime you all see this kind of notation, x of t or y of x or y of t or whatever, v of t, this is something that took me a little bit to appreciate. This represents a function. You've heard that phrase before. Functions are machines. That's the way to think about a function. It's a machine. And I heard that phrase and it didn't make sense to me after time went on. This is a machine that when you put in time, it spits out x. That's all this notation means. X of t means when I put time into this equation, I get x. If it was instead y of t, it'd be when I put time in, I get y. I get my y location. If it's v of t, that means when I put time into this equation, it spits out the velocity at that time. It's a subtle thing. It's something that people kind of just like look over, and you've seen it so much. But if you understand what an equation is, what a expression is, it helps you out. All right. So great. This is an expression that says, hey, if I plug in time, it tells me my x position. It tells me where I'm located, left, right. Now I want you all to plot this. I want you all to make a graph of this. Try it out. You know, it's going to be a graph. And the first thing you're going to have to decide is what are my axes? What are my labels of the axes? And then you'll try to plot it. Try it out. I'm going to give you all like a minute. This is an important skill. Try to graph this equation. As stupid as it sounds, it's useful. The first thing I'm going to want y'all to do, make sure you label what these axes are. What is each of these axes measuring? If you don't have those labeled right, the rest is terrible. Like, it's going to be awful. So to give you that piece, my dependent variable always goes on the horizontal axis, and x is my vertical axis. That's my independent variable. When I put t in, it tells me my x. And this is generally, most of our things will be time is actually our horizontal axis. As time goes on, what happens to something else? All right, so there's two ways to plot this. There's two ways to think about this. You can remember that the equation that this matches the form y equals mx plus b, and you get slope and all that goodness from there. The other thing is you can just make up numbers. That's the easier one. You can say when time equals 0, what's my x? So I could say when time equals 0, what's my x? 4 minus 2 times 0, that equals 4. So at time equals 0, I'm located 4 meters, positive 4. We can then do another data point when time equals, and I'll even make this a little bit more clear, when time equals 0. When time equals 1, 4 minus 2 times 1, that means I'm at positive 2 meters. And, if you want a third data point, you could do time equals 2. Oh, I'm just picking random numbers. These numbers aren't anything fancy. I know this question doesn't actually ask us to find these things, but this is going to help us understand all of this. And there's my line. That is the equation. That is this graphs. So there's a saying, a picture says 1,000 words. An extension of that is a graph shows 1,000 data points. Graphs are super useful to express a bunch of data in a concise way. And so it's useful for us to be able to read those in physics. And one of the reasons I want it, so there's lots of reasons, I'm going to keep referencing this because we need to be able to read this graph and understand what's going on. I will walk out this, I will actually act out this graph to help us understand what's going on here as well. But our first question says, at what time does the particle cross the origin? And one of the things immediately that people can get confused with is if you think that the origin is here in the middle, we never pass it, but that's not the answer. The origin here is not at the intersection of these two axes, and that's something that confuses people. So let me actually write out a little bit here. I'm going to erase this without erasing everything, but that's really tricky to do. Oh, so close. All right, great. I did it. Good job, me. All right, so step one. So I've drawn a picture. A graph is effectively a picture in its own way. So I did step 0, draw a picture. Step 1, what's given? The equation. Couple things I want to point out while I'm doing this. There's some tips for how to write letters. This is going to sound stupid, but it's so useful. When you write a T, notice I put a little tail on it because if I write a T like this, it looks a lot like a plus sign. If you put a little tail on it, it makes it not look like a plus sign. These are little things. If your notation is clear, you're less likely to make a mistake. If your notation is not clear, it's hard. Another thing that's useful is when you're writing 7. Sometimes when I write 7 really quickly, I can accidentally put a little tail on it. Looks like a 2. That's not great. What do I do to make that fix? I put a line through it. I always put a line through my 7s so they don't look like 2s. You don't need to do any of these things, but it just makes your life. I have found them to be useful. When I write a 0, I put a line through it. I say that. I didn't put a line through the one down here, but I need to be. So that way it doesn't look like an O. Tiny little things that you'll see me do that people generally don't mention, but I'm going to mention because they're things that you pick up after doing a lot of math and you make a lot of stupid mistakes like think a T is a plus sign. And you notice that other people do this. Same thing with Z's. Z's, I put a little line through so they don't look like a 2. So tiny little notation stuff that you'll see me do throughout class. Point it out now. All right, great. What are we solving for? At what time? So time equals question mark. But specifically, when am I finding the time? The origin here, again, is not the center of these axes. The origin is when x equals 0. The origin is based on position, not time. Like, what is the 0, 0 for time? Beginning of the universe? I don't know. What do you define that as? When we talk about origin, we're talking about a position, a location. There's only one variable for location here. It's x. So what is the origin? When x equals 0. Not when time equals 0. That's not what we're referring to. When we're talking about the origin, that's when x equals 0. And so then, fairly straightforward. Great, we got our equation. I'm just going to rewrite it again. Normally we'd write another equation. So when is x equals 0? Well, just make x equals 0 and let's find out. So you get -4 equals -2t. You get t equals 2 seconds. And look, that matches on our graph. At t equals 2 seconds, that's when we hit x equals 0. All right? So to help understand this graph a bit more, because this is a skill we need to develop, I'm going to act out this graph. So at time equals 0, so I have to define the origin. First, I have to tell you where the heck the origin is in physical space. The duck is going to be the origin. He's the origin. That is 0, 0. That is x equals 0. When I'm located where he is, I'm at x equals 0. When I'm to the right of him, I'm a positive x. When I'm to the left of him, I'm a negative x. So this is 0. So at time equals 0, I am located at positive 4 meters. So at time equals 0, I don't know if I have enough room. 4 meters is roughly over here. Positive 4 meters. After 1 second, I end up at this pink dot. Where's that located? We actually calculated that. That's at 2 meters. That means 1 second later, I'm 2 meters to the right of the duck. Another second later, I'm at x equals 0. Another second later, I'm over here. So long story short, if I put all those pieces together, if I walk out this graph, that means I start at 4 meters. and I am moving to the right at a constant velocity, or the left at a constant velocity. That's what this graph represents. It is an extremely useful skill to be able to look at a graph and be able to understand physically what it's representing. And that's a physics skill. And that's going to come up in these slides. It's going to be one of the things I'm going to ask you about. We're going to see it, but this is our first example of that. All right, cool. Graphs, things. Next question. What is the displacement of the particle between t equals 3 seconds and t equals 6 seconds? Make a new slide, copy all the good things over. So I'll copy the question itself. Copy that, and then I'm going to copy all my hard work because I don't want to rewrite it. Boom. I'm going to delete most of it. All right, great. So we're solving for something different here. So we delete steps 2, 3, 4. What are we solving for? When you all are writing these steps 1, 2, 3, 4, what you are doing is you're taking the problem, which is written in English, and you're translating it to math. Math is a language. You need to know what the translation is. When it says displacement, that is the symbol delta x. So when you're doing these steps, and we're going to see a lot of practice for this, you're taking the words and you're translating it to math. Delta x is what we're solving for. That's what displacement is. That's the symbol for displacement. Oh, I forgot to mention this. Delta, this triangle here, I'm actually going to go back and show it in displacement because I forgot to tell you all this. This symbol is the Greek letter delta. You might know that if you're in Greek life or anything like that. There's only 26 letters in the English alphabet. We got way more variables than that we need. So we go visit the Greek alphabet and we steal a bunch of their letters. This is delta. It's a triangle. Anytime you all see this symbol, anytime you see this in our class, it's always going to mean the same thing. It's going to mean change. Delta is always change. So in our case, delta x is x final minus x initial. It is always the final minus initial, always. Anytime you all see this, delta x, that's my change in position. Delta v, change in velocity. Delta a, change in acceleration. Delta f, change in force. Whatever. Put it in front of something and it's the change. This is going to happen a lot in this class where we have various Greek letters. And if at any point you're like, I sometimes take these for granted when you've been speaking a language for so long, you're so used to it. I do my best to remember to point out these things, but if ever there's a variable I introduce, you're like, whoa, where did that come from? What does that mean? Just ask me. I can almost guarantee you 10 other people have the same question. So, all right, so delta x, that's displacement, change in position. So what's our equation for this? Well, delta x is x final minus x initial. So then we just got to find those things. We got to find the final. Oh, and we do know a couple things. We know our t initial is 3 seconds, and we know our t final is 6 seconds. It's going to sound like a stupid question, but it's a pretty common one that I'll get. And it's not a stupid question. It's just when you think about it, you're like, oh, okay. How do we know which one's the initial and which one's the final? Smaller time is always initial. Final time is always a bigger time. Final and initial are always defined by a later time is final, and earlier time is initial. Always. Always. Exactly what you would like it to be. But you need to be careful on this. It's very common to mix these up. Very common. So just remember, ask yourself, what's the beginning, what's the end? The initial is the beginning, final is the end. That's how you make that decision. So we're going to find x final. That's x at 6 seconds. And so that's just going to be 4 minus 2 times 6, which is going to be -8. I only got that answer super quick because I've already done this math this morning. X initial is going to be x at 3 seconds. Equals 4 minus 2 times 3, and that one's going to be -2. So delta x is just -8 minus -2, which is -6. The negative is meaningful, and I'm actually going to write this answer 2 ways. So this is a correct answer. Delta x equals -6 meters. Great, that's the answer. Let me translate that into words for you all so that actually you know what it represents, because it does represent something in words. -6 meters means that my location is 6 meters to the left of where I started, of the start. You don't need it, I'm not going to ask you that in a test, but that's what it means. -6 meters means I was somewhere, and at a later time, I'm 6 meters to the left of that. Negative means I went to the left. Positive means I went to the right. It's a very, very, very important thing. Going to the left 6 meters is drastically different than going to the right 6 meters. Going east versus going to the west is drastically different. A rocket going up or a rocket going down is drastically different. Positives and negatives tell us which way we went. -6 is not a smaller number. That's the thing that people fall into the bad habit of, is they think of negatives as smaller numbers because that's what you've been trained on for so long. -6 is a smaller number than -3. In this class, -6 is a bigger number than -3 in the sense of if you moved -6, you moved farther than if you moved -3. You just moved farther to the left. Okay? So the negative, it just tells you direction. The number tells you how much. Small thing, but big thing. All right. Great. There's a slide that had that already. All right. On to the next concept. We'll see. Hopefully get through velocity. And then Thursday we'll get to acceleration and the equations. All right. What is Demoduk's velocity right now? I'll give you 20 seconds to think about that. Just think about it in your head. There he is. Check him out. He's on the desk, chilling, sitting still. Well, maybe sitting still. All right, what say you all? What's his velocity? 0 meters per second. With respect to what? The room. With respect to the room, correct. 0 meters per second. Relative to the sun, he's zooming. I don't know what it is. It's really fast. The Earth is going quite fast. So again, there's actually an infinite number of correct answers depending on what you refer to. But there you go. Velocity. What is velocity? Clearly you all have a sense of it. It's how fast you're moving and in which direction. Mathematically, it's your change in position. How much does my position change every second? So the units are meters per second. We take our displacement, we divide it by the change in time, boom. That's how it's your average velocity. If this was the engineering class, we could do a derivative and get the instantaneous velocity, but you're spared that. We'll only do average because you don't know. Most of y'all probably don't know derivatives, and that's fine. You'll get by plenty fine and write it down. V for velocity. It's a vector. Positive means to the right. Negative means to the left. Positive is to the right. Negative is to the left. And the units we're going to use in our class are meters per second. They just come from the math. What's the unit for displacement? Meters. What's the units for time? Seconds. Ta-da, there's the units. And if you've never thought about, in your car, 60 miles per hour. It's one of those things you've seen all the time. You might have thought about this, maybe you haven't. If you're going 60 miles per hour, that literally means in 1 hour you will travel 60 miles. 30 miles per hour means in 1 hour you'll travel 30 miles. 10 meters per second means in 1 second I'm traveling 10 meters. Positive 10 means I'm traveling 10 meters to the right. Negative 10 meters per second means every second I'm going 10 meters to the left. Same speed, just different direction. Positive 10 meters per second, negative 10 meters per second, you're going the same speed, just different directions. And a touchstone for you all, I forgot to actually mention this during my last class. You don't need to have this memorized, but it's useful. Remember, anytime you solve a problem, you should try to ask yourself, does it make sense? I've been doing physics for a super long time, and before I taught this in the spring, if someone asked me how fast is 1 meter per second, I guess I could kind of walk it out, but like, if someone told me something's traveling at 40 meters per second, I have no idea. Like, I had no sense of whether that's like how fast that is. I'm like, that's probably pretty fast. 40 meters in 1 second, that's probably pretty good. But like, how fast? I don't like have anything to kind of hold to. So the number I'm going to give you all, I did this unit conversion because I thought it was useful. 27 meters per second is about 60 miles per hour. Really, really nice. You know how fast 60 miles per hour is. If you've been driving cars or around cars, you have a sense of 60 miles per hour. So now you have a sense of meters per second. If something's going 27 meters per second, that's 60 miles per hour. If you're solving a problem and you find that the answer, I say, hey, how fast is this person walking? And you get an answer of 20 meters per second. If you remember this little thing, that's roughly 40 miles per hour. Nobody is walking at 40 miles per hour. Something's wrong. That's useful. Like, that's a nice, remember, you're gonna make mistakes. The more tricks you have to catch your mistakes, the better. And so that's a really useful touchstone that I use all the time now. If something's traveling 50 meters per second, 50 meters per second is roughly twice that value. Well, 2 times 60 is 120 miles per hour. Now I have a sense of how fast they're going. Learning is all about connecting new things to things you already know. That's what makes things stick, at least for me. This is something you know, connected to something new. All right. What is, I don't know what the heck, why this is here. What is the average velocity? This wording is really weird. So let's look at this one. Position particle. I'm going to put this one after this later one, actually. Between 3 and 6 seconds. We'll come back to this one, but I'm going to fix it for now so I don't forget to later. All right, great. Not going to worry about this one. We'll get a chance to practice that in a bit. All right, object starts at x equals 2 meters, ends at x equals 10 meters. If it takes 4 seconds, what is the average velocity? See if y'all can try it out, make sense of it. Again, feel free to check with people next to you. If you have a different answer, one of you is wrong or both of you is wrong. Anytime with these, check. All right, so I'll leave the answer responses, the ability to answer that open. We're going to go through the problem-solving process. So if you're still answering, that's fine. It'll still stay open. So again, I'm going to translate this. This is a problem that you may not need to actually write all these steps, but I'm going to always do this just to show you all modeling how to do it. So it starts at x equals 2. But is that my beginning or my end? You all tell me. Beginning. So we put a little x naught next to that. I can't have 2 variables with the same label. That means 2 things mean the same thing, and that doesn't make sense. If I said x equals 2 and x equals 10, 10 does not equal 2. Doesn't make sense. All right. So what is this one then? X equals 10. What variable does that go with? Yeah, xf. All right. What about this 4 seconds? What variable does that go with? Is it just t? And if so, is it my beginning t? Is it my final t? It's my delta t. The better you're able to translate these things, the better the problem's going to go. If it takes 4 seconds, that's my total time that passed. That's my change in time. All right, step 2, we're solving for velocity average. Step 3, we find the equation that relates these things together. Velocity average is change in x over change in time, which is xf minus x naught over delta t. Step 4, plug and chug. 10 minus 2 over 4. One of the most common mistakes is putting final, second, and initial first. So people doing 2 minus 10. Super common. It will happen to you. I've made the mistake a bunch. You'll make the mistake. It'll happen. The more you write, the less likely you are to do it, because by writing it down, I can check, XF is 10. Trust me, writing stuff down just makes your life easier. There's a reason humans invented the written knowledge. It's a thing. Yeah, let me just be careful. Yep, 2. Great. If you haven't gotten the answer yet, it's too late. Great, we did it. I'd actually forgotten about that. So, 2 meters per second. What does this mean? It means every second, the position is increasing by 2. I'm getting 2 meters farther away from the origin every second. All right, I'm not going to bother with this one right now. I might upload it later. So remember, translating things is important. Sometimes in problems, variables will not be given in numbers. They'll be given in words. And this is something that's going to sound obvious once I say it, but it's something you're going to have to recognize. In a problem, if at any point it says something is at rest, stationary, still, not moving, stuck in place, anything like that, that means in your givens, you should write the velocity equals 0. Now, you need to make the decision, is that the beginning velocity or the final velocity? Is it saying it starts at rest, or is it saying it ends at rest? You need to clarify it. So is Vf equals 0 or V not equals 0? Something is 0. One of the velocities is 0, and that's something you have to translate when you're solving this. This last problem, all the givens were listed as like numbers. That is not going to be the case in most problems. I'm prepared for that. So these are key phrases. The other key phrase that you're going to want to look out for is constant. Anytime something's constant, and we're going to see a problem like that coming up, keep that in mind. So let's see. All right, so velocity versus time graphs, position versus time graphs. Something I want to point out, the slope of a graph on position versus time, that is rise over run. If my x-axis is position, so if my x-axis is x, my vertical axis is x and my horizontal axis is t, and if I say that v is delta x over delta t, that's rise over run, i.e. that's the slope. So if you have a graph and I say, what's the velocity at some time, and I will ask questions about what the velocity is at some time, you're going to find the slope at that point on the graph. If you're looking at, this one kind of shows the velocity versus time, and it's a slope here, slope here, slope here. These dotted lines are because you can't find the slope of a cusp. A sharp point, there's no slope of that, so that's why those are there. But don't worry, I'm going to ask a problem about this at some point. There's some on the problem sets as well. It says the word integral. That's a calculus thing. Don't worry about it. If you know what it is, great. If not, don't worry about it. Velocity is a vector. It has direction and magnitude. So velocity versus speed. It's like displacement versus distance. Velocity, vector. It matters how fast I'm going and in which direction. Speed, only care about how fast you're going. Cop pulls you over, they ask how fast you're going. They're asking for your speed. You'll just give them a number, 70 miles per hour, 60 miles per hour. If you told them I'm traveling 70 miles per hour northeast with an angle of 30 degrees east and north, they're not going to care about the second part. In physics, we do. In physics, we care about the direction. We're most commonly going to be working with velocity. Again, so many examples of why it matters which way you go. Like, I think I've given enough examples for that, so I won't try to come up with another one. But positives to the right, negatives to the left. Still true. Okay. So let's try this one out. So this is the last problem we're going to do today. We'll work through it. I'll give you all some opportunities. So a cyclist rides 8 kilometers east for 20 minutes. Then he turns and heads west for 8 minutes and travels 3.2 kilometers. Next, he drives east again for 16 kilometers, and that takes 40 minutes. What's the final displacement? What's the average velocity? The first thing I want you to do, so let me show you all this. You all do not need to know the card. So this is never eat soggy waffles. Super useful way. You do not need to know this for this class. On a test, I'll just say up, down, left, right. I'm not too worried about whether you know north, south, east, west. But it is nice to know that. If you don't know that, it's a useful thing. So there you go. You got east and west. East is to the right. West is to the left. My first thing I want you to do is draw a picture of this. Draw an arrow. They travel 8 kilometers east. Draw an arrow that represents that. Then right after that, right where that one ends, draw an arrow that's 3.2 kilometers west. Then after that, draw an arrow that's 16 kilometers east. Tip to tail, tip to tail, tip to tail. I'll give you all like a minute or so. Try that out. If your picture's bad, your problem will be bad. We're only worrying about the distance right now. We'll get to time. All right. So I told you all east is to the right. So we're going to start drawing an arrow. Doesn't matter where you start. You get to pick the origin. I'm just going to pick it right here. So we're going to make an arrow. And I am going to actually immediately convert my units. The second you see kilometers, that should be a flag should go up in your head saying I need to convert that to meters. So do that. I'm going to do that immediately. How do I do that? I chuck an e I multiply it by 1,000. So 8e3, otherwise known as 8,000. All of these are true, but I'm just going to leave it as 8e3 because that takes less writing for me. And it's easier to do, in my opinion. Great. Now, ideally, the next arrow would go right on top of this. I guess I can try to do that, though it's going to look a little rough. Maybe pick a different color than that. I'll do blue. So now I'm going to travel 3.2 kilometers west. 3.2 is roughly half the... 3.2 is approximately less than half of 8. Approximately. It's less than half of 8. So 3.2 E3 meters. They travel backwards. And then I need to draw one more arrow on top of everything where I now travel, and this is a little messy, but it does the job. 16 kilometers. That's not a big enough arrow. It needs to be twice as big as the first one. The better your picture is, the better your final result is. And there we go. What was the reason for drawing this picture? This question asked for the displacement. What is the displacement? It's the distance from where I began to where I ended. So from this picture, it helps us understand what we're actually calculating. Pictures are useful. They help us understand these things. So that's delta R, or if you want, same thing as delta X in this case, because it's only one-dimensional. So I'm going to write my laundry list of givens here now. And I'm just going to call X1 how far I traveled to begin with. That's going to be 8e3 meters. I'm going to call T1 how long that took. 20 minutes. A flag should go in your head. Minutes is not the base unit for time. The base unit for time is seconds. So we're going to multiply that by 60. So that is 1,200 seconds. Always do unit conversions the second you write down a unit, because otherwise you might forget. And if you forget, well, your answer is going to be wrong. So the sooner you do something, the less likely you are to forget it. In my life, I've learned that every person's different. X2 is negative. So left, direction matters. Time is always going to be a positive quantity. No such thing as a negative time. Negative time means you're traveling back in time, which while the math lets you do it, we're not doing it in this class. x3 is going to be 16 E3 meters, and the time 3 is going to be 40 minutes. So 40 times 60 is going to be 2,400 seconds. I'm going to double check on my calculator. Even though it's a simple calculation, it runs the risk of me making a mistake. It's always better to do things on a calculator than in your head. You will learn this for yourself when you make enough mistakes. All right, step 2, what are we solving for? Delta x. In this case, how do I find delta x? It's final minus initial. Delta x is final minus initial. So my question is, what's my initial? What's my final? My final is going to be x1 plus x2 plus x3. My initial, I'm just going to decide it's 0. I start at 0, then I go somewhere. And then you go from there and you solve this. I'll copy it to the next one, and then we'll quickly zoom through the last bit and get you all out of here. The cool thing is, once you've written down all your givens, and once you've written down step 2 and 3, I never have to read the problem again. Once I've translated it, I don't need to read the original, assuming you got everything. So step 4, delta x is just going to be 8E3 plus negative 3.2 E3 plus 16 E3. All the E3s just get, it's all the same base unit. So 8 minus 3.2 plus 16 equals 20.8 E3. That's 20,800 meters. And the last thing we need to do, so that's great. Part A done. Yay us. Part B, it's actually pretty quick. Once you've done steps 1, 2, and 3, that's the hard part. So for part B, we are solving for the average velocity, V average. So that's step 2. Step 3, what's the equation for average velocity? It's delta x over delta t. You have delta x, delta t. I'll let you just add the times together. I'll let you all try that out. The final result is 5. The final result, you should get 5.1. Oh, last thing I want to point out, there's a little bit of a rounding thing here. 5.1 is more accurate, but the answer here says 5.11. And people always ask, what if I put 5.1 instead of 5.11? As long as you're within 1 to 2% in this class, you're good. I don't actually care about the final answer. I only use this to check your work. If you're within 1 to 2%, that means your process is good. I don't care about all the exact rounding or preciseness or things like that. I care about the process. So 5.1, that's within 1 to 2%. You're good. All right, y'all. See you Thursday. Good luck on things. I'll stick around if you have questions. Upload these slides, all that good stuff.